So thanks everybody for coming. My name is Ada Weiss. I'm from Eer5, one of the co-founders of Eer5. And Eer5 is a new type of content delivery network that is based on users, and also it is web-based. So we're going to touch a lot of JavaScript and WebRTC stuff. Who's familiar with WebRTC? Just everybody. Okay, so we can skip that part pretty fast. Yeah, so WebRTC is an API definition. It's not necessarily code or implementation. Google and Mozilla implemented it at the beginning, but formally it's an API for real-time communications. And now it is already baked into the modern browsers. We have Chrome, Firefox, and Opera. Luckily, IE is also getting there with ORTC. Surprisingly, they did some really nice work, and they are working together with the rest of the browser vendors. So it looks optimistic at the moment. WebRTC is an interesting open source project because first of all, it is open source under the BSD license, and browser vendors all work on it together and take it as it is and implement it in the browser. But also, I'm not sure if there are any other projects that cost that much, because Google spent almost $200 million on companies that they acquired back in 2010 in order to get high quality codecs, which they just open sourced everything. It was audio codecs, ILBC and ISAC, and also VP8, which is it is part of WebM. Quite recently, Cisco opened H.264, which is now also mandatory in WebRTC. So in that terms, I think it's an interesting open source project. But we're not going to talk about these codecs. We're going to talk about Data Channels API, which is the little brother of the main API. The main API talks about audio-visual capabilities, like building a Hangout application so we can talk one-to-one using audio and video. The other part of the API is called Data Channels API or Data API, and simply let you transfer any arbitrary data between two endpoints, peer-to-peer. And it's a full network stack. Okay, so every browser up until recently had a stack that is based on TCP, and now we have a really rich stack that is based on UDP. It's pretty exciting. It's UDP as a transport layer, and then I stun and turn to do the NAT traversal. And on top of it, we have SCTP and DTLS for the secure layer. And on top of everything, the data channel protocol itself. And as end users, as developers, we use Data Channel API directly, but there are a lot of stuff going on under the hood that WebRTC is doing, and I'm not going to go too deep on that. I want to say why we think it's huge, because so we have another full stack that lets us build wonderful things, and especially it can fix this. I mean, the web was supposed to be very decentralized. From the beginning, everybody wanted it to be decentralized, that no component would be too crucial, too important. But unfortunately, things are too centralized today. Everything is dependent on web servers. Even if we want to build simple chat applications that just communicate between one endpoint to another endpoint, we need a server to do that. We need WebSockets or HTTP And that's kind of a limitation that we have today. Um, and it caused us as developers to build a lot of logic into the server side. And it's not really necessary, and it's actually harming the performance and the architecture as a whole. WebRTC will hopefully solve this and make the web fully distributed, and we'll see more functionality going into the endpoints, into the client side. How does it work? So you know WebRTC. I'll go quickly on this one. So it's not as easy as a client-server communication where you just open a connection to a server. Two random computers in the internet cannot just communicate without a third party to help them with the discovery and opening up the firewalls and the NATs. So just quickly, WebRTC sessions begin with signaling from the initiator to the server in a signaling channel. Many people use WebSockets and Node.js here. Very easy to implement. Once the metadata is transferred between the two endpoints and they actually want to start the direct channel between them, they need to do the NAT reversal, which is done in ICE, either using turn servers, which are basically a relay, or using stun, and that's what we're trying to achieve most of the time. The stun opens up the firewalls, and the two browsers can communicate directly. What can we do with it? So this is the trivial use cases: send files, send metadata in games or other things, text. But we're talking about media today, and for media, probably need a mesh network, which is a network with more than two nodes. We like to think about three types of mesh networks: the full mesh, where everybody are connected to everybody, and the overlay tree, and the partial mesh network, a dynamic mesh network. In practice, people use the right one. And the use cases for this are varied. It can be games. I don't know if you heard about CubeSlam or the games Mozilla built. In video, new companies are building really interesting applications today, like TalkBox or Room. BEMTV is an interesting live peer-to-peer solution. Audio solutions, file sharing. We have a project named Eer5, and it's also built with these mesh networks. Okay. But usually it's not enough. Usually you want to complement this mesh network with a server. We're not against servers, although we said we believe the web should be more decentralized. It doesn't mean that servers are now obsolete, obviously. And the two technologies can really work together well. If you think about it, peer-to-peer normally needs servers for the beginning, before the content gets popular, and for sourcing the content. On the other end, servers are hard to scale. They are expensive. They have errors. They can break, and it's harder to replace them with something else, with more servers. So the mixture between these two kind of bring something new to the table with infinite scale. It is more resilient to problems. It is faster and lower latency. Now, as a user of this network, I can get content from closer sources. The latency compared to the server is lower, and it's cheaper. It's cost effective to build something that is based on us, the users, compared to pouring more and more resources on the server side. So how can we build a WebRTC CDN? There's a little, there are two meanings here. WebRTC CDN can mean also a CDN that supports WebRTC. That's not what we're trying to do. Trying to build a layer on top of the servers that caches content in this mesh network and can build a high throughput delivery network. And that's what we do in Eer5, and it needs to be easy to use. So if I'm already using a CDN or I'm already using a few data centers, it needs to be easy to add another layer of cache. It needs to be agnostic to all sorts of web servers and all sorts of HTTP implementations. Tricky part also is to work in different use cases. It needs to be secured, so no malicious peer can get in the middle and send me some content that I don't want to get. Obviously, it needs to be fast and scalable, so it would be helpful to use it. And open source here helps a lot because some of the problems are solved by other people. For instance, security. If you build something in JavaScript, you run under many layers of software that limits you in a way, which is sometimes more difficult, but in a way it makes sense because it makes easier to secure these kinds of applications, and Google and Mozilla spend a lot of time to make sure everything is encrypted and works very secured. So we don't need to re-implement it and reinvent the wheel, as opposed to previous peer-to-peer solutions that were in the market that had to implement everything, all the encryption layers, all the data layers. I mean, we can't break too much. We can't do too much harm. So we use a lot of open source projects, and I'll go over the architecture of our solution. So the origin HTTP media server can be any HTTP server. It can be a CDN, whatever. That's the existing components. And we add the complementary peer-to-peer components. So on the back end, in red, it's our tracker. It's a signaling layer. It's a NAT reversal layer. And it's also simply a CDN that serves our JavaScript, so we can actually do what we're doing. So when the Eer5.js is loaded from our CDN to the browser, it connects to the backend using WebSocket. It will get matches to other peers that can contribute to the content delivery. From there, the peer can connect to multiple peers, and it will begin a connection session with other peers using the standard WebRTC process, which includes signaling and NAT reversal and whatever is necessary for the two peers to communicate. Once they are connected, they can exchange metadata and data independently, which is very efficient. It's very low latency. It works well, and the server, the tracker is not worried about that. So I try to show a demo. Let's see what happens.
Do you need the audio?
No. I don't have internet.
Trying to connect to Wi-Fi legacy as the FOSDEM legacy nodes.
Okay, let me just show something small.
Could you get the Wi-Fi? Which Wi-Fi are you connected to?
That's okay. I'll skip the full demo. So I don't know why this frame was picked. Interesting screenshot. But it was the demo I just ran, and this represents the actual chunks that I received as a peer, and I actually construct the buffer on the fly from the various sources. It's not real-time streaming. It's a buffer that is constructed from like pseudo streaming construction where chunks are received, and it can be from multiple sources. And if one source suddenly disappears, it's okay. We will get a chunk from a different source. Let's continue. Okay. Okay, but this is our problem today. Uh, Maybe someone else has the same problem. Most of the video applications today are working in a way that the native player, the video tag, whatever, is connected to a media server in a way that we can't break the connection. Like video video tag with src x.mp4 will means that the video tag will just fetch contents from that resource, and nobody can touch it, nobody can intercept it, and it means that just one server will be responsible for the delivery of this file, and we don't want that. And we want full control. We want multiple sources. We want to have prioritization and other features that will make the delivery more efficient. So we believe that the world needs to shift from a native playback, a native delivery, to something that is more JavaScript-based, application-based delivery, where we have more control as developers. Luckily, it's already happening with Media Source API and Dash. So the model of native HTTP agent that fetches content from the media server is changing from that to something that is based on a video player that has some JavaScript logic that fetches content through XHR, through XMHP request, and then pushes it to the player. It's much better because it lets us also build more mechanisms in the client side, build more distributed smart applications. We can build better analytics in the client side. We can prioritize between the video chunks. We can control the bandwidth. We can have multiple slots, multiple connections even to a single server, or we can use several servers at the same time. We can do smart prefetching and all sorts of interesting JavaScript logic very easily. Instead of just fetching content using XHR, we can use WebRTC. We can do offline storage. You can use Eer5. And the end result is that it's a more distributed approach, which is, we think it's smarter. There are a few enablers to make this happen. Media source extensions, obviously. Dash with Dash.js, and I was happy to hear the guys from all the players that are actually implementing it, and it's very important for them. MP4 box from Gpack also helps a lot because you can take a progressive MP4 and on the fly change it to something that media source extension can actually play. If you want to use Flash, if you want to use HLS, then you have two choices, either with Flash, and then you need something like FlashLS, players like Clapper or Video.js that already bridges between Flash and JavaScript, and we can make the request from the JavaScript, bring it back to Flash. Kaltura made a great open source project called Nginx VOD module that changes MP4 progressive on the fly in the server side to HLS, and then if you mix it with the FlashLS or something like MSC with HLS, then you can go to JS-based delivery model. MSC to HLS is an interesting project. Video.js is now focusing on that actually let you do this without Flash. So you get HLS chunks and push it into MSC. We decided to go with an API that is very similar to XHR. Actually, it is compatible with XHR. So we can bake our API into that JS and other technologies that are JavaScript based. So it's just the same API. You can check it out on GitHub. And to sum things up, we want to move from this model to something that is JS delivery based, and then we can hook in and do delivery even in complex media use cases. That's it.
Thank you, Adam. So are there any questions? Comments, remarks?
Something?
Clear?
Like me, you were very clear.
Yeah.
One question.
I have a question about, you talked about CDN, and what I understand, you kind of complementary to the offer of CDN. So what is your rank? Because from what I understand, since there are some peers that applies to content where they have many viewers, you can relate to that. So what is like trying to know
Yeah.
Just repeat the question.
So you mean what are we trying
how can
to,
you help?
how can we help an existing CDN?
Yeah.
Yeah, so
For your customers or
yeah, so
what
I
are you
think
trying to achieve for them?
I think this slide probably answers that the most. So CDNs are great, but they don't have infinite capacity, especially not in places where they are not based. They don't have POPs. Uh, so even Akamai, the best CDN in the world, failed several times in large live events or in places where in Asia or Latin America where the doesn't have that many capacity. And also it can be expensive. So some people today are not using CDNs. They won't use a CDN because it's too expensive, and they can use something like that.
And just another view. So from where I live, the connection that we have is asymmetric, which means that we have much more bandwidth for downloading than for uploading. We have some caching system so that people can keep uploading even if the internet is downloading.
Yeah, so that's one of the challenges when you build this kind of solution, because we are dependent on the sessions, the web sessions. So if you close the tab, you are not sharing anymore, and that's why we designed the algorithm to be very sensitive to that. It works from the beginning. You're becoming effective, and what we're trying also to do is when you navigate from pages within the same domain or from different domains, we'll try to share as much as possible. At the same time, we try to keep the resources, the users safe. We're not trying to abuse anyone. So it's a difficult challenge, but in many countries the bandwidth is symmetric now, and the upload has really increased recently. Yeah.
Do you tell the user, because
some people pay for the bandwidth and stuff like that. I mean, you cannot abuse their connection.
Yeah. So we limit the amount of bandwidth that we take, and we try to not use our upload capabilities in mobile networks. So we do GeoIP detection, and if it's a mobile ISP, we're disabling the upload links. Yeah, so yeah.
I'm curious, how do you decide whether it's the server to serve the chat or a peer or several peers?
So the question was how do we decide if it's a peer serving the content, the server, or both of them? So usually it's both of them. It depends on the use case. If it's video, for instance, usually it starts with server because the latency at the beginning of the session is better to the server before we do all the signaling and connecting to other users. So usually the first chunks are fetched from a server, and then we try to fill the buffer of the playback as fast as possible using both of them. Once we reached a safe margin, we can use peer-to-peer only. There are other use cases where you do all the time both of them because we want to achieve the highest throughput. Yeah.
How do you, let me think of the best way of putting this. I can imagine a scenario where a user on a maybe not a mobile network, but their connection is degraded. So in chunk formats like HLX and Dash, players will just go down to the lower bit rates so they can really use chunks faster. Connection hopefully gets better. They can move up bit rates and get a bit of better video quality. How does the interaction between grabbing data from server and peer affect that chunk formats?
In the consuming perspective?
Yes.
So the question is basically how do we integrate with the adaptive bitrate algorithms? We haven't done it yet, so it's something we're about to do now. But our goal is to, because we add throughput to the end user, our goal is to achieve higher bit rates using the peer-to-peer. So imagine that you have a capped connection to the CDN, and you cannot get more than 1 megabit per second. It doesn't mean that with peers you cannot get to 2 megabits per second. And that's what we're trying to achieve now and aim for the higher bit rates. Cool. Last one. Yeah, so the browsers are not asking the users. The API works in a way that it's transparent. I can tell you later on the reasons, but so it's basically up to the content provider to decide how to communicate with the user about it. It can be an opt-in mechanism that only if you approve, you're becoming part of it and you benefit from it as well. But it's up to the publisher to decide. Cool. Thank you.